Hi, I'm Janani. Today, let's discuss about what magnetic fields are and the effects of a magnetic field. Let's find out whether they're good or bad. Let me begin with a brief introduction of magnetic field. So now, what is a magnetic field? A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. Similar to how an electron field surrounds a charge, we can consider a magnetic field to surround a magnet. For better understanding, we draw magnetic field lines to show the presence of magnetic field around a magnet. So here is a bar magnet. It has a north pole and a south pole. The entire region around this magnet can feel the presence of this magnet's field. This bar magnet's magnetic field might be felt even beyond the screen. This is how the magnetic field lines of the magnet is shown through these circles or ellipses. They appear to be straight lines in the center, but they aren't. They elongate to become circles. The magnetic field is even felt inside the magnet. The green arrows here show the direction of the magnetic field. They always move from the north pole to the south pole of the magnet. These magnetic field lines never meet or intersect each other. If they did intersect at a point, it means that the two directions of movement are possible for the magnetic field. Everything in this world is made up of atoms. An atom is the bound state of at least one electron to a positively charged nucleus. The electric attraction between the electron and the nucleus pulls the electron inward, while the rules of quantum mechanics prevent the electron from collapsing down completely onto the nucleus. In this case, the relevant rule of quantum mechanics is the Heisenberg uncertainty principle, which says that if you confine an electron to a volume of size r, then the electron's momentum must become at least as large as p, which is approximated to h by r. Here, h is Planck's constant. This itself is a huge topic which needs a video on its own. The corresponding kinetic energy is p squared by 2m, which is approximated to h squared by mr squared, which means that the more tightly you try to confine an electron, the more kinetic energy it gets. Here, m is the electron mass. This kinetic energy is often called quantum confinement energy. In a stable atom, the quantum confinement energy, which favors having a large electron orbit, is balanced against the electric attraction between the electron and the nucleus, which pulls the electron inward and has energy which is approximated to E squared by E0r. Here, E is the electron charge and E0 is the vacuum permittivity. In the balanced state, these two energies are nearly equal to each other. What do magnetic fields do to free charges? They pull them into circular orbits. The force with which a magnetic field pulls on a charge is given by a force of B, which is approximated to EVB, where B is the strength of the field, E is the electric charge, and V is the velocity of an electron. For an electron moving at a million miles per hour at the inside of an atom, this works out to be 1 piconewton per Tesla of magnetic field. Now, we can consider the following question. Who pulls harder on the magnetic field? One can see that just for about any realistic situation, the force provided by the magnetic field is much, much smaller than the force from the nucleus, so that the magnetic field essentially does nothing to perturb the electrons in the atomic orbital. However, if the magnetic field were to get strong enough, then the force it produces will be enough to start significantly bending the electron trajectory, and the shape of the electron orbits would get distorted. Studying force of B greater than force of E from above gives the estimate that this kind of distortion happens only when B is greater or equal to 10 to the power of 5 Tesla. Given that the strongest static magnetic fields we can create artificially are only about 100 Tesla, it's probably safe to say that you're unlikely to experience this anytime soon. But supposing that you did wander into a magnetic field of 10,000 Tesla, what would happen? Strong magnetic forces would start to squeeze the electron orbits and all the atoms in your body. Let's take an example of a spherical hydrogen atom. Here, B is the strength of the magnetic field. As B increases, we see the atom's orbits getting squeezed in the direction perpendicular to the magnetic field and would look like this. Further, increasing the magnetic field strength, the orbits get squeezed further, ending up to cigar shape to needle shape. Similarly, the molecules that make up your body are only able to hold together when they are made up from normal-shaped atoms and not needle-shaped atoms. So once the atomic orbitals got sufficiently distorted, the chemistry would change dramatically and these molecules would start to fall apart, and your body would be reduced to a dusty incoherent mess. But don't worry, you won't become dust. If your body is really subjected to strong magnetic fields, something would probably go wrong biologically far before the field got so large, such as 10,000 Tesla or more. For example, the motion of ions through ion channels, which is essential for nerve firing, might be affected. Thank you.